Here's a population model. Looked on census.gov, and the U.S. population right now is about 315,000 people, and there's one birth every second and one death every 12 seconds. So the birth rate, I calculated that by taking 60 seconds divided by those 8 births. That gave me how many births per second. And then to find the birth rate, I divided that by the number of people. So I got estimates here for the birth rate and the death rate. So B for birth, M for mortality. Okay, so we're going to ignore immigration and just figure out how long it's going to take for the U.S. population to double. Now we've got this model here. If Y is the population, dy dt, well, it should be growing by the birth rate times Y, right? So we calculated the number of births per person in a minute here. So we did 60 seconds, so this is births per minute per person minus the number of deaths per minute per person. If you look at this, I can factor out the Y, and I have the birth rate minus the mortality rate times Y. That fits this model, dy dt equals ry. So we know the solution to this differential equation will be yt equals y naught, the initial population, that is, times e to the, now my rate is the difference between the birth rate and the mortality rate. You can see that in general, if the birth rate is higher than the mortality rate, then the population is going to grow exponentially. If the birth rate and the mortality rate are perfectly matched, then the population will just remain constant. And if the mortality rate is higher than the birth rate, then the population will decay exponentially over time. Okay, so let's see if we can figure out how long it's going to take for the population of the U.S. to double. So, oops, that should be a t there. Okay, so if we wait till a doubling time, I'll call it t sub d for doubling time, then we know that the population we have will be twice what we started with. So the doubling time only depends on the birth rate and the death rate. It doesn't depend on how many you start with. It's kind of a feature of exponential growth and decay. Let's see, so we take the natural log of both sides. We get the natural log of 2 equals birth rate minus death rate, so the net growth rate. Okay, and we're looking for the doubling time, so the doubling time would be the natural log of 2 divided by the difference in the birth and mortality rates. So let's estimate the doubling time then by putting it in our calculator. I've got my birth rate, which is 2.3778 times 10 to the negative 8. Okay, and then I'm taking away my death rate, which is 1.5852 times 10 to the negative 8. So there's my net growth rate, and I want to divide that by the natural log of 2. So divided by 2, take its natural log. Okay. Now what I calculated was b minus n divided by the natural log of 2. What I wanted was the reciprocal of that. So I'm just going to use the reciprocal key on my calculator. I get a pretty big number. That number is 87,452,332. So 87,452,332. 87,452,000. Oh, I forgot already. 452,332. 332. Okay, but what are my time units? So I took 60 seconds and divided by 8 seconds. So I got, okay, so that was a time, 60 seconds divided by 8 individuals per second. So should have got something with units of, 60 seconds per minute, right? So I have a birth rate in minutes. Okay, so I have birth rate in per minute, so I just found the doubling time in minutes then, because of the units here in b minus n. These were rates they were per minute, and so you take the reciprocal of that and you get a time in minutes. Okay, so now it'd probably be more interesting to us to figure out how many years that is. So what I'm going to do is convert this. I know that there are 60 minutes per hour, and I know that there are 24 hours per day, and I know that there are about 365.25 days per year. So if you look at what I'm doing here, I have these days are canceling, these hours are canceling, the minutes downstairs here will cancel the minutes upstairs, and so I'm left with something 1 over year in the denominator, so that's going to be a number in years. So I need to divide by 60, by 24, and 365.25. So I take my number, divide by the 60, and then I'm going to divide by the 24 for the 24 hours per day, and then I'm going to divide by 365.25, and I get a doubling time of 166 years. So approximately 166 years until the population is double, so that would be when we'd hit about 600,000.